Okay, I finally got around to making this video for the problem 6.1. So we're going to do the steps I used to create this. So this uses the payload card. So I think we talked about this quite a bit in class, so I'll just go through the steps. So I started Hypermesh, and I think by now we're familiar with this. So again, I get the user profile prompt, and I make sure it's set to Optistruct. And let's make the screen a little bit bigger. And so again, just as a reminder, I'm going to go through and create the material properties, then create the element properties, then the mesh, the boundary conditions, and then finally the load cases. So here, the material is not specified because, again, unless you're dealing with non-homogeneous statically indeterminate structures or ones where you're looking for the deformation, you don't really need to know the Young's modulus to get the stresses from a mechanics and materials approach, but we do need those for doing the FEA. So I'm going to use aluminum since we use that a lot. So I'm going to go into the right window here for model. I'm going to create material, and I'll call it aluminum. And again, down here, we can put the elements for the property card. So Young's modulus for aluminum in imperial units is 10 million psi, 10 e to the 6th, and Poisson's ratio is 0.3. And so there we go. It's created. So, another interesting feature, which I don't believe I showed, but maybe it's a good time now. There's this idea of looking at the card edit, okay? And you'll see it in a couple spots. You'll see it down here. This is a card edit. Let's see what it should give it. Yeah, card edit. And even if I right-click on the material here, you'll see I get an option for card edit. And when I do that, I get, the Mat1 card exactly like it's in the Nastran manual or the Optistruct manual. So you can directly see the input card to make sure what you're doing in Hypermesh is really what's happening in the solve, okay? All right, so that looks good. Now let's create the I-beam property, or the T-section property, I should say. And remember, so it's going to be a property. Call it T-section. Now remember, you could use the P-bar-L card. And, I really should do a video where I do that. But in this particular case, since I used the 4 stress recovery points going down the y-axis, I didn't do that. So I'm going to use a p-bar property. So we're going to change the property, the card image, from a p-shell to a p-bar. It should be somewhere here. It always gives me that warning. I don't know why. We'll set the material to the one we just defined, aluminum. And remember, we calculated here all the geometric properties, right? So area is 0.6. This up to the side. And so I'm going to type these into the field here. Oops, there it is. So the area is 6 square inches. I want, now remember, we talked about this in class. I'm going to make the element orientation vector up in the vertical direction, in the global y. And so that means that this plane here is going to be my plane 1. So the I that resists bending in that plane is actually the I about this element z-axis. And that's the larger of the two. That's the 8.5, right? So I1 is going to be 8.5. I2 is 2.5. I1's not always the biggest. It depends on how you define it. You have to be, that's why I'm saying it really benefits. I did it on the slides, but it benefits to take a piece of paper, draw the global axes, draw your element axes, the orientation vector and the resulting element axes, and then determine the planes and what the appropriate eyes are for those, okay? J is 1.65. The stress recovery, well, there's no C on this one, right? J is 1.65. And there we go, we're good, right? So we're good. All right, so next, let's create the mesh. So I'm going to create a component. Remember, these are just like layers. Again, I'm just going to have one of them, but normally you're doing an aircraft structure, you're going to have tens to 100 different components, right? Even more depending on the complexity of it. So you can specify the property here, but it actually doesn't hold over for 1D elements. And so there you go. So let's now create the nodes. So I'm just going to type those in. The first one is at 0, 0, 0. The second one, I forget the coordinates. I think it's 48. Where is it? Okay, so 30 inches would be 30. This next one's going to be 36 in the X direction. So let's resize. So there are the two of them. Then the next one is 40 inches from there. So that is, wait, what am I doing? I'm so sorry. Say 30. It's not 36, it's 30. I'll delete that one later. Then the next one is 40 on top of that. So that is at 70. Then the next one is 30 after that, right? So that's 100. And then the last one's 30 past that, which is 130. So right there we go. The 1, 2, 3, where is it? Last one. There it is. Okay. And so I want to delete this one. So I'm going to go in and do temp nodes, and I'm going to pick this one and clear it. And so now it's gone. All right. Okay. So I have the nodes, and so now we're going to create the 1D elements. And for this model, right, the orientation is going to be in the global Y. So I'm going to do that under 1D. And we're going to create a bar element, so I click on bars. Now, let's be careful. Well, we have the orientation set as the y-axis, that's correct. Let's change the property to be the T-section property we defined. And the element type, we're not using a C-beam, we're going to use a C-bar. And so there you go. So now let's define the nodes. Now remember, to get this correct, I really need to pick the nodes going down the x-axis, because that would make sure that the element x-axis is pointing in the same direction. If I pick this node first and then this node first, that would, go the other orientation, and then actually the z-axis would be flipped. In this case it doesn't matter, but in some cases it does matter. So we'll pick this one and this one. This one, and then this one, and we will return. So there you go. So we've got the mesh made. Well, let's color it by the component level, so they have the same level as the component. You could also change it so it's colored by the material. In this case, the material was blue, and so they're all the same material. Or you could check it by the property as well. And this is really useful, again, if you have multiple materials, multiple properties, to make sure that you have the right ones assigned as you need to. Okay, let's do the boundary conditions. Let's first do the SPCs. So I'm going to make a load collector called SPC. That's going to have the point constraints. That's active. So again, we do constraints under analysis, and we are going to we're going to create nodal constraints. Now make sure you don't have all 6 degrees of freedom. In this case, the model has a pinned connection at the second node and the last node. So if you constrain the rotations, that's going to be like built in. So you will get a very different result. So, as always, the application of these boundary conditions can be a bit subtle. So you want to be careful of that. So we don't want to have all 6. I'm going to release the rotational degrees of freedom and make them pinned. And again, it's the second node and the last node, and I'm going to create that. And there we go. I guess we can get rid of all the temporary nodes now. And we're good here. So I'm going to make 2 load cases. I'm sorry, not 2 load cases. 2 load collectors for the forces. Because I will first make a load case where we apply the loads, that we calculated that are exact for the distributed load. And then I'll do one with the P load 1 card, right? Which is what I recommend that you do, okay? But just at least to show that they are the same. So I'm going to create 1 load collector called equivalent forces or equivalent forces, because these are the forces that are going to be equivalent to the distributed load. All right, and let's create those. So let's recall what those would be. So first, let's put the point forces on. So it's going to be 300, 700, and 400, all acting in the y direction. So again, we're going to go under analysis, forces. They're all in the y direction. The first one is going to be 300 pounds. So that's at this node. The second one is 700 pounds at the second node, which really doesn't have an effect except changes the reaction forces. And then the last one is 400 pounds. And that's at this node. I will create that. And while I'm at it, I'll create the, I know it's not part of the distributed load, but let's add in the 2,000 up force at the 4th node. So this would be 2,000. Again, it's acting in the y direction, and it's right there. Okay, and you can see they all scale accordingly. All right, so we got those, but now we need to add the moments, okay? And remember, 2 of them are going to be acting around the positive z-axis, and one's going to be in the negative z-axis. Right? So if you look at this model here, right, the moments at the first and second node are going to be about, in a right-handed sense, acting around the positive z-axis, and then the moment at the third node will be acting in the negative z-axis. So to create those, it's what's called a moment card. It looks very similar to the force card. You just pick a magnitude and a direction. So the first one is 1,500 pound-inches, positive, and it's going in the z direction. So I'm going to make this z. It's supposed to be left over before. Create that, and there you go. It's in the positive z. It's a little hard to see here, but you can see the arrow is pointing that way. That's the double arrow thing. The next one is 1164. So I'll change this to 1164. And it is at node 2. Did it not create it? It said it did. Let's try it again. There it is. I don't know why I did it that way. And then the last one is in the opposite direction, but 2,667. So it's going to be negative 2,667 because it's in the negative z direction. It's acting at this node. And There it is. Okay, so we've got them there, right? Let me just double check that I got the right values. 1500, 167. Oh, my gosh, it's too early in the morning. I screwed up. So I actually have the wrong value. This is 1167. I did 1164 for some reason. So what I'm going to do is I'm going to change that. So I'm going to go from create to update, and then I'm going to pick that one. Hopefully pick that one. There's a couple there, so I'm going to make sure I pick the right one. Pick that one. And this is going to be 1167, right? 1167. And okay, and then we can change that to update. So that's going to change the value, and it's going to ask me what I want to change. And for this one, it's the magnitude. So I'm going to change the magnitude. And there you go. So it has that. All right, let's save this. It's not saved there. Well, okay, and that's great. So that's what we want. Oops. All right, so this will work. But let's make another load case, or another load collector. Excuse me, another load collector. But this is for the pload one. So it's going to use pload one. Okay. And just to make my life easier, I'm going to turn off the visibility of this other load collector. So I'm going to click on this little finite element meshy looking icon, and you can see they disappear. The new load collector is defined, and it's active because it's bold-faced. So to do that, these are like pressures, okay? And considers a pressure as a distributed load. And we can pick the elements that they act on, the magnitude, all that sort of stuff, and the type. So this is set to a pload 4, but we want to change that to pload 1. So done that. And it's going to be the same, and we're going to put it on these two elements. The magnitude is 20, and it's in the positive y direction. And so we're going to create those. Okay. Good. We still need to do the 2,000 pound force, because when we do the load cases, right, I mean, we're going to use that 2,000 pound up force in both load cases, so it has to be in this load collector as well. So I'm going to add that as well. So this is going to be 2,000. Well, it's already defined there. There it is. Great. Okay, and so we're good. We got them all here. Now, this is a bit of an unfortunate thing with the pload 1 card. It doesn't quite by default define them correctly. So let's look at this. So here is the pload card definition, right? So this is what we use for the pload card. So the way it works is you can define a distributed load over a segment of a one-dimensional element, and that distributed load can linearly vary. So what we do is we define 2 points on the element. Most often they're going to be the grid points, but you can actually offset those. So that uses this x1 and x2 feature, and then we define the values of the distributed force at both of those regions. So actually, what I should have here, I can actually type this in. We should have x1 set to 0 and x2 set to 1. Now what that means is the 2 points are going to be A and B, because 0 corresponds to A and 1 corresponds to B. We're using this fractional distance definition, so it's more convenient. Excuse me. So the fractional length is kind of defined here, right? All right, so those are the 2 points we're defining the pressure on. And we have the same pressure at both. So here we should have a 20. And here we should have also a 20. Okay. All right. Now the other things, we have a set ID and element IDs, can take care of those. Now type is an interesting card. It's not written here, but type tells you which direction. Maybe I should just load the. Maybe I'll just load this up. Let's just do. We do pload 1, and here we go. This just gives you all the information. I should have put this in. This is a little better. So type tells you how the force is defined. So the most convenient one is to use this FXE, FYE, FZE. So this is saying like the distributed load is in the X, Y, or Z direction for the element. You can also do it in the global, but it's easier to do it in the element. Or you could also make a distributed moment. And so if you use MX, MY, MZ, or MXE, it's going to do a moment. And then scaling, we're going to set to fractional. Scaling is what determines how x1 and x2 are defined, and so we're going to use fractional. So here, we're going to have the load going F, it's a force, it's going to be the y direction in the element y direction. So I'm going to use FYE there, okay? So this value here should be FYE, and this value here should be fractional since it's going to be fraction. So those are the values that should go into that card. I'm going to make it red just to stand out. Okay? All right. Now, that's what we want. That will make a uniformly distributed load in the y direction of 20 at both grid points A and B. All right, let's see how that works. Did it do that correctly? So to do that, I'm going to do a card edit. So I want to look directly at this card for that element. So I'm going to pick, I'm going to hit this little icon here, card edit. And you can do card edits on a bunch of things, nodes, elements, blah, 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 right? So we want to do it on a load. So I'm going to pick load. You got to say what type of load it is. So for us, it's going to be a pressure. It's a P load 1. And now let's pick the load. If I can get it. I think I got it. Is it there? I think I got it. Let's see. Okay, and so here you go. So here's the actual card. Now the problem is, you see it's got FYE and FR correct, but it didn't specify X1 or X2, nor did it specify P2. So I need to change these, okay? So this is actually not too hard to do, but I need to change this to be 0, this to be 1, and to put 20 there, okay? So let's return, and here's what I'm going to do. I'm going to pick both of them. Let's get it. I believe I got both of them. And I'm going to set x1 to 0, x2 to 1, and this to 20. And now when I hit return, it's going to update both of those. So like if I do card edit here, and let's look at that one. Yeah, you see it's correct. Likewise, if I hit this one, it's also correct. So good. We're set there. So I've got those correctly defined. Okay. Card edit's super useful for a lot of things. So that's why I made point of showing it here. It's really good to do. Okay. And I think we have everything. So now I can define the load cases. I have to do two load cases, right? One's going to be for the point equivalent forces, and the second one's for using P-load. So let's create one load case. Load step. I'm going to call this equiv force, because that's what it's using. It's going to be a linear static analysis. The load collector for the SPCs is on the one called SPCs, and this one is using the point forces. So I'm going to, for load, I'm going to pick equivalent forces. And so we've got those defined. So we're good, but remember, we always, for the 1D elements, we want to write out the opti files, the ASCII files. So I'm going to go under here and change output, and we will output, for what it's worth, we'll do the displacements, put those into an opti file. We will output element forces, that's always useful. The next one is the SPC forces, right? That's usually the SPC forces. And then lastly, the stress. Okay, so now they're all there. And, right? So you can see. What's going on here. Right. Yeah, so it's got them all. That's good. Okay, and that's using the load collector for equivalent force and SPCs, using that case. So now let's make another one that uses the P-load. So I'm going to make a copy of this. I can actually do that. I can duplicate this. Oh wait, I'm sorry. Why did I duplicate that? I don't want to duplicate that. Like that. Sorry. Let's delete that. I want to duplicate the load step. Let's duplicate this. So I'm going to right click on it and say duplicate. And the reason I'm doing this is because this will have all the outputting stuff, so just a little faster. And I'm going to call this P-load, okay? P-load 1. And what we have to change here is the load collector from equivalent force to P-load 1. So it'll use that in that step, okay? And now we can save. And now we should be ready to run. And I haven't had any coffee today, so let's hope that this works. So we hit Optistruct, right again, it's under analysis, Optistruct. And let's see if we get any errors. Nope, it worked out. So let's look at the results. Again, we're looking at the hyperview. You know, in the slides and in class, I went through looking at the opti file, so I won't go through that. Like I said, we did that in class. But let's just look and see that the results are hopefully the same. If they're not, actually, that will be good, because then I'll make another video where we show that, okay? All right, so here we have the load case for the equivalent force. We can also set it to P-load, right? So let's look at the first one first. We'll do the first load case. Let's change that up here. And like we normally do, let's make it a deformed plot. So I'll set the scale to like 50 and put apply. Move that toggle bar over, and yeah, it looks like it's deformed roughly correctly. That's a good look, and it does it really fast, so we're going to change it to slow it down a little bit. And let's shade it. So I'm going to we're going to shade it with the stresses. And here, there are a lot of options. So we can look at the axial stress, right? So that is going to be the P over A stress, I believe, right? And so that is 0. There is no axial force on this at all. So that comes out to be 0. Okay? So the axial stress is 0. we could look at the longitudinal stress at stress recovery point C. So these are the stresses at point C. Wait, why are those here? Are these the actual ones? Oh, I'm sorry, yes. S stands for stress recovery point. A is for axial, and then obviously at the 4 stress recovery points. So these are all going to be 0. It's kind of odd they have these because they're going to be uniform for these elements anyway. So they're all 0, right? And that makes sense. Now, if we go down, you can also look at the max and min axial stresses. They're 0 as well. So the next group, we can look at the bending stresses. So the stresses in bending at point C. So we can apply that. And that's also 0. Why is that 0? That makes no sense. Oh. I know why. Okay. This is perfect. So this is very good. So they're all 0, right? This is what I made the mistake that I always talk about in class. And I did it here. So all the stresses are 0. Well, this is useless. The reason the stresses are 0 is because when I did the property for the CBAR element, I did not define any stress recovery points. So it can't calculate the stresses. So it has the deformations, but no stresses. So this is actually quite good. So let's fix that. I should say I did this on purpose, but I did not. I just screwed up, okay? All right, so let's not save this session. Let's just go back, close this out, close this. So yeah, it has no way of calculating the stress recovery points, right? Or calculating the stresses, because I have not given it the stress recovery points, right? If we go back to the slides. Remember, I had wanted to calculate the stress recovery points at these 4 points, right? Using these coordinates. I did not define F, C, D, and E. So let's do that. So, right, so here's the property. Remember, well, that's the component. So let's look at the property. Where's the property? Here's the T-section property. I didn't define the stress recovery points. Remember, to show those, you hit this continue 1 that shows you the second line. And so now I can change all these, right? And remember, the Z coordinate is going to be 0 for all of them, and then it's 2.5, 0. So this is 2.5. This is actually 0. This one is minus 0.5, and this last one is minus 1.5. Right? Just double check. Yeah. All right. So now we have the stress recovery points. That should be able to do it. Actually, we can also look at the card to make sure it's correct. So if I right-click on here, I can do card edit, and here you can see the card shows up in exactly the same format that we expect. Where is it? Here. Where's the P? Oh, I didn't show the P-bar card here, but that's okay. But you can look it up in the other slide deck, and you can see it's exactly the same. It's got the stress recovery point, so that's good. Let's rerun this, and now we should get some stresses. Okay, so let's look at the results. Yeah, so let's go back, make the form case 50. Let's look at it from the side, because that's pretty much where we are. Now let's look at the stresses, and oops. So let's look at the bending stresses, say at point C. I might apply Now I have the bending stresses. So I can see the bending stresses at point C. I can see the bending stresses at point D, which are 0, right? Because that is at the neutral axis. Well, you know what? I'm sorry. I screwed this up. I did. Point E is the neutral axis. Why is it showing up at point E? These should be 0. I gotta screw this up. Yeah, I think I screwed that up because I must have did I do these correctly. Let's look at this card again. Yeah, I said D is 0. D is because it's I did it the wrong way. All right, let's get this correct. I'm so sorry. You see what I had done here is I defined C as the top point, where here I'm actually calling F the top point. So I did this reverse. So let's fix that, and I will do this correctly. So I'm going to close this out again. And normally I would stop the video. I would make a new video, but I'm not going to do that here. I'll show you how to do these things and change them. All right, so this is supposed to be minus 1.5. This is supposed to be minus 0.5. It's not that it's wrong, it's just that I want to make sure it's consistent with the way I labeled them in the slides, right? So F is the top point, right? So F is this point. So this is at y equal to positive 2.5. I was just thinking, I don't know why I labeled C at the bottom and F at the top. That's what I did. So this is going to work. Let's save it. And let's run it a third time. And now we should be good. Let's look at the results again. Set the deformation plot to 50, although you don't have to do this, but I always do this it's just another one of these things that kind of gives you a bit of a sanity check as to whether your results sort of make some sense. And, that's the way we expected it to be deformed. So let's look at the stresses, and so now, right, if I look at the stress recovery points in bending for point E, that's the one on the neutral axis, so that should be all 0. If we look at point F, which is at the top, that should be the highest ones. So the max here is 129, 12 KSI is the highest. 13 KSI. And so we can also look at the max overall. So this is going to be the S bending max. So that should be the same values. And they are, right? Because the bending stresses are going to be maximum at the top point, point F, right? The bending stresses are going to be highest here because the distance from the neutral axis is the greatest. And so that all looks good. So let's look at the second load case. And when you hit apply, you can see actually nothing changes. And that's good. For once I got something right. And that's because the loading for P load is exactly the same. They're mathematically the same as when we put the point loads on. So they should give you the exact same results. And they do, okay? You can check the Opti files and you'll confirm that, okay? So, okay, good. So that's where we're at. So again, I apologize for screwing it up a couple times, but I guess it is useful. So remember, we need to define the stress recovery points everywhere. If not, you get no bending stresses, which I didn't do. Also, you should take care to make sure you put them in correctly so you don't make mistakes, because it's easy to do, which I did. but we fixed that, and now we're good to go. Okay, so you got to see the card edit feature, which is super useful, as well as you know, checking your results. Okay, all right, very good.